Okay, we're going to pick up where we left off yesterday working with trig substitution, and we're going to start with an example here so you can continue your notes from yesterday if you want to. We've got the integral of 1 over the square root of 2x minus x squared. So what I want you to observe here is this is a little different from the three forms we were looking at yesterday, but again we can't do a u substitution or anything like that. So we're going to have to get this into the form we were working with, and the way we're going to do this is we're going to complete the square. So kind of on the side of your paper, let's go ahead and do the work to complete the square with what's under the radical. So I'm going to rearrange this and take the negative sign out of both terms, and then you remember to complete the square, that middle number of negative 2 has to be divided by 2 and squared. So we add 1, and notice I'm leaving it inside the parentheses. And also notice, because there was a negative in front, this means I've really added a negative 1 here. So to balance it, I need to add a positive 1 on the outside. So what's in the parentheses gets factored, and if I rearrange it, I get this expression, and that's going to be what's under the radical. Now I did a little small u substitution here, and I said let u equal x minus 1. So du, of course, is just dx. And I rewrote my integrand in terms of u, just to make it a little bit easier to work with. So let's set up our triangle. Since we have the expression in the form a squared minus u squared, a is going to be the hypotenuse this time, u is the opposite side, and the square root of 1 minus u squared is the adjacent. So think about the substitutions we need to make here. We need an expression for the radical, and we need an expression for du. So this time I've used cosine theta as the expression for the radical, so that's just the radical over 1. And then we need an expression for u. So think about what trig function would work best in this situation. Sine of theta is equal to u over 1. And then we need an expression for du. So just like yesterday, we're going to take the derivative of this expression, and du turns into cosine theta d theta. So if we go back to our integrand and make the appropriate substitution, the numerator becomes cosine theta d theta, and the denominator just becomes cosine theta. So simplifying out the cosines, we just have the integral of d theta, which of course is just theta plus d. Now remember, as we talked about yesterday, we have to go back to this expression in terms of x. So since sine theta was equal to u, that means theta is arcsine of u, and recall that u was x minus 1. Let's do another one, and this is also going to require us to complete the square. So I'm going to take the denominator, the way I did this is I rewrote the 2 as 1 plus 1. And in doing that, this actually makes this a little easier to work with because the first 3 terms here give you a perfect square trinomial, and that breaks down to 2x plus 1 quantity squared plus the 1 I had out here. So if we go back and replace our integrand with this new expression, we get this. And just like in the last example, I did a little u substitution just to make the work look a little neater on my page. So I let u equal 2x plus 1. So I get an expression of 1/2 in front of the integrand. Now, this doesn't look exactly like some of the ones we've been working with, but we can still use the triangle with the u squared plus 1 under the radical in the hypotenuse. Take a look. Tan theta is opposite over adjacent, or u over 1. So taking the derivative of that, because I need an expression for du in the integrand, we get secant squared theta d theta equals du. Also observe that secant theta is equal to the square root of u squared plus 1. And I need the square of this radical in my integrand, so I'm just going to write that as secant squared theta. So take a look at my new integrand. The numerator just becomes secant squared theta d theta, and the denominator becomes secant squared theta. So I'm just left with the integral of d theta times the 1/2 that we had earlier, and that's 1/2 theta plus c. Now, just like in the last example, we can't leave theta in our answer, but remember that theta was, or tangent theta rather, was equal to u. So I'm going to rewrite this as arctan of u, but keep in mind that u was 2x plus 1. Now, you may have noticed in this example and the previous example, we both ended up with an inverse trig function. And actually, the formulas you learned last year in Calc AB were based on this idea of using trig substitution. So this expression here, this formula we learned last year as the integral of that is arctan, we could have done using this triangle technique. And the same thing for arcsine. Let's look at another example. So here we have the integral of 1 over the square root of 4x squared plus 1. Okay, so let's take a look at the triangle setup for this problem. So we've got the radical, since it's 4x squared plus 1 under the radical, is the hypotenuse. 2x is the opposite side, and 1 is the adjacent side. Notice that secant theta is the square root of 4x squared plus 1. And tangent theta, which is opposite over adjacent, is just 2x. So if I get my expression for x, I have x is equal to 1/2 tan theta. And of course, we need an expression for dx. So we're going to take the derivative, and dx turns into 1/2 secant squared theta d theta. When we make the substitutions, my integrand becomes secant squared theta d theta on top, with just secant theta on the bottom, and I have a factor of 1/2 out front. Simplifying, we get the integral of 1/2 secant theta d theta. You'll notice this integral of secant theta has come up a lot, so make sure you know this one. The natural log of secant theta plus tan theta. Then, of course, go back and make your replacements. Secant theta was the square root of 4x squared plus 1, and tan theta was 2x. Let's look at another example. So we have the integral of 1 over x squared plus 1 to the 3/2. At first glance, it may not look like we could use trig substitution to do this, but remember that x squared plus 1 to the 3/2 is really the square root of x squared plus 1 cubed. I'm going to go ahead and set up my triangle according to this expression with the square root of x squared plus 1 as the hypotenuse. X is the opposite and 1 is the adjacent. I started out with secant theta, which is hypotenuse over adjacent. That's your expression for the radical. And like always, we need an expression for x so that we can get an expression for dx. So tan theta turns into x, and dx just turns into secant squared theta d theta. So when you make the replacements, you should get secant squared theta d theta on top and secant theta cubed on the bottom. So that simplifies to cosine theta because that's just 1 over secant theta. And then, of course, the integral of cosine theta is just sine theta plus c. And then make your replacement for sine theta from your triangle. Sine would be the opposite over the hypotenuse. So we get this expression as our final answer. So far in this section, the only type of problem we haven't done is a definite integral. So let's take a look at one. So we have the integral of the square root of x squared minus 3 all over x from square root of 3 to 2. So we're going to set up our triangle with x as the hypotenuse, square root of x squared minus 3 as the opposite, and square root of 3 as the adjacent. So I started off by making an expression for sine theta. Notice that sine theta is just the square root of x squared minus 3 all over x, which is the original integrand, but we still need an expression for x. So I use secant theta as x over the square root of 3 and solve for x. And remember, we need to take the derivative. So the derivative for secant, of course, is secant theta tan theta d theta. And then, I always like to change the limits of integration. So the lower limit was x equals square root of 3. Well, we need everything in terms of theta, don't forget. So I put that x equals square root of 3 into this expression right here for x. Then we're going to solve that for theta. So the question you would need to ask yourself here is, where does secant theta equal 1? Remember, secant is really 1 over cosine. So where does cosine equal 1? And that would occur where theta equals 0. We need to do the same thing with the upper limit of integration. So if x is equal to 2, we get an expression like this. Divide by the square root of 3, we get this. And you need to ask yourself, which angle has secant equal to 2 over the square root of 3? Remember, that's really saying, where does cosine equal square root of 3 over 2? And that would be at pi over 6. If we put it all together, our new integrand turns into this. We do a little simplification on this, rewrite it in terms of sines and cosines. We get the integral of tan squared theta. Now, we talked about how to integrate this the other day. Remember, tan squared theta is really just secant squared theta minus 1. That we can integrate because we know the integral of secant squared theta, which is just tan theta. And, of course, the integral of 1 d theta is just theta. Using our new limits from 0 to pi over 6, we get a final answer that looks like this.